My name is Margarita Vald. I'm from Tel Aviv University and Intuit, and I'm a cryptography researcher, not data scientist, okay? I'm going to tell you today about some security problems that we have in the way we use data, but I'm also going to tell you how to solve them, and everything in 10 minutes, I promise. Okay, so let's start. Well, I don't think I really need to motivate the benefits of data. I guess we all know the advantages. We really care about having clean data, have good quality data, have a lot of also quality, quantity. But if we won't take care about secure treatment of data, the next thing to happen is that we'll have a major data leakage. And this data leakage can be unintentional, but it also can happen by malicious attackers that attack our system actually on a daily basis. And to understand why this is the situation where we are facing right now, let's take a look how data is treated in companies. And this is true also for Intuit, but also for other enterprises. Okay? So data is stored in what called data lake. It's a centralized storage that all the data is stored there. So let's see an example. We have here an application that that needs to save data. For example, sensitive data. So what's going to happen is that the data is going to be encrypted and stored in this data lake, in this centralized storage. On the other hand, we have many applications that need to use this data, right? Analytics, machine learning models, and they need access to this data. So the data is going to be decrypted, and the sensitive data is going to go straight to the application, okay? And the situation is that we have many such applications, each one of them touching vast amounts of data. So putting the hat of security person, this is not a great thing to have. Why? For me, it's enough to break into one application and to get a full access to the whole storage of the company, actually, okay? So I will say that each one of these applications is a potential vulnerability point, okay? And my goal is to reduce the attack surface, to convert as many applications as possible to operate on sensitive data in a way that protects the data, okay? Good, so here is a crazy idea, try to follow me. Let's say that instead of decrypting the data, I'm going to give the data encrypted to the application, and I won't give the application the ability to decrypt it. Magically, let's say, just imagine, magically, the application going to operate over the encrypted data without seeing the actual data, and it will return me the encrypted result. So in terms of security, I'm really happy. Okay, problem solved. Now the application don't have any access to the actual data, only to the encrypted data, and encryption protects the data, right? Amazing. So this is my goal. I want to follow this crazy idea and try to modify applications to operate over encrypted data without seeing the clear text data, okay? And the question is how I can do it, how I can make machine learning models operate over encrypted data. They are so related, like they need the data, right? Okay, great. So that's what I'm going to tell you about. And I'm going to give you a really high level of our approach, how we do it. And the full details can be found on ePrint. It's public archive. Amazing. Okay, so we're going to focus on specific machine learning models, which are decision tree-based models. And they are very popular at Intuit, but they're also popular in other places. And what we're going to do is, as I said, we're going to follow this approach of using encryption, modify the algorithms to operate over encrypted data. Okay? And we're going to use a specific type of encryption called fully homomorphic encryption. This encryption allows to do some mathematics, basic mathematics, additions and multiplication. What do I mean by that? So if I'll add two encryptions, I will get an encryption of the addition. If I'll multiply two encryptions, I'll get a result of the multiplication, an encryption that encodes the multiplication of the values. Okay, great. So what I'm going to do is I'm going to take the algorithms, I'm going to identify parts that are not addition and multiplication compatible, and I'm going to replace them with a sequence of additions and multiplications. And I'm going to do it in an equivalent way. What do I mean by that? I want the algorithm, the new modified algorithm, to give me the same result or approximately the same result, okay? And also, another important thing, I'm going to minimize the running time. I want this sequence of replacement to be as small as possible because operating over encrypted data has cost. Security has cost. This is reality, you know. Okay? So this is my 2 goals. Okay, and what I'll do in the rest of the talk, I'm going to give a simple example how we're doing this for replacement, algorithmical replacement, for comparison, which is a basic building block in decision trees. If we want to do decision trees, we will have to take care of comparison, right? Okay, so what is a comparison? Basically, it's a step function. Let's assume we're comparing with 0. So it means if my value is greater than 0, then it evaluates the function, evaluates the 1. Otherwise, it evaluates to 0. Great. As I said, you must solve this to do decision trees, but on the other hand, it doesn't look nothing like additions and multiplications, right? And to operate over encrypted data, I need additions and multiplication. So what we're going to do, not surprisingly, we're going to approximate the function, and we're going to approximate it using MSE error, mean square error, L2 norm, but we're going to, as I said, we need to have, we want to minimize the overhead, the running time overhead. For that, we need the sequence of replacement to contain as little as possible additions and multiplications. So to have the polynomial, we need the polynomial that we get to have the smallest degree possible without compromising accuracy. So to do that, what we're going to do is we're going to give different weights along the interval. Sorry. We're going to give different weights, as I said, along the interval. In particular, we want around the step to give weight 0. It means, in a sense, I don't care to have errors around the step, and we will give higher weight, like further from the step itself. So here is an example of how the function looks like for different degrees and different don't care window where we give weight of 0. So as I said, every time I need to use comparison, instead of using this function, I'm going to use a polynomial. This is an example of degree 15, for example, using this technique. And if I need to compare at step theta, for example, then I will use the function gx minus theta, and it will be approximately 1 if x greater than theta, and otherwise 0. So what I want to say is just to mention several challenges that we still have. And the most, in my opinion, challenging thing and hardest to achieve is to have better collaboration between data scientists and security. Okay? And this is like very important and necessary to achieve solutions that are best of both worlds. Otherwise, I don't see how it can be done. Another thing is that I mentioned that we have a running time overhead, but we actually also have, using this approach, a storage overhead as well. And we're going to publish a solution for that soon. And the last thing is that it would be really nice and challenging, I think, to apply this approach to more advanced models like neural net training. And this is an open problem. Nobody did it. And so I want just to say, so the approach we're taking for security in data science is actually modify your algorithm to work on encrypted data. This is the approach, and this is what I mentioned. Thank you very much.